It is going to be similar. The final is going to be similar. Let me see whether I can do a share screen with you. Let me see whether I can find it. So this is output of something from that my son demonstrated to me. So he take a picture, and then it really nice. It get rid of all the background and everything. So it format it for you and then put it in one file, and it's really pretty. So this is from the Cam Scanner app. There are many different apps there you can find which are free. One is called Adobe Scan, maybe free, I don't know. You can just take a look. Yeah, it's pretty nice. Yeah. So you guys should really try different things and to make sure it works. So for example, here, this one, all the background stuff they get rid of it for you. Okay. It's just pretty easy to use. It seems just take a picture and then they just have the whole good stuff there. Then I can actually you submit it through Canvas, and I can go in, I can mark it up. I actually can mark it up, and I can even type some comments there if I want to. Okay, and that will be the right way to do it. Because I got about half of the class send it through email to me, and some of them in like 6 or 7 files. So it's kind of difficult for me if I want to combine them into a single file for each of those, it takes me a long time. I actually did that. I spent like 2-3 hours, was able to did only like several students. So I decided not to do it anymore. So, okay. So I will post something online, and then you can just try to play around. Doesn't matter what file you have. Just practice it and then try to submit it and make sure it's reasonable size. Okay. So that it will go through.
So you'd rather it be like one PDF file, is that?
One PDF is good. It would be the best.
Okay.
If you have to have multiple PDF, that's not the end of the world as long as it's inside Canvas. So if it's like question 1, it's one PDF. Question 2 is one PDF. I can still handle it pretty easily. The preferred one is one PDF. Okay, especially if it doesn't name it correctly. Okay, all these are just names which are some random numbers. Then I don't really know which one is which. Okay, I don't know whether I have graded a particular problem or not. So if you use some apps and combine all of them, this particular app that it's actually able to combine multiple pictures in one single file. Okay. All right, so let's stop sharing and go back to chapter 6. Any question? So the test was pretty hard, but I add 20%. So people are doing okay now, I think, in general. So the class average is now 78. What we have done so far this course, we talk about linear independence and dependence. We never talk about lengths and angles. This concept of inner product. Inner product is the same as dot product. It's just a different name. allow us to talk about lengths and angles. Okay, so I'll just quickly go through the definitions and so on. Oh, by the way, if you have done calculus 3, you know this already. Okay. So it will be 1 times 4 plus 2 times 5 plus 3 times 6, 4 plus 10 plus 18, 32. It's okay? That is called the inner product. Okay, so inner product. Another way to think about this is that this is actually in matrix notation. In matrix notation, it's the U transpose times V. Okay, now this is a matrix multiplication now. Once I write it like this, this will become 1, 2, 3, 4, 5, 6. And this will be matrix multiplication. So it will be 1 times 4, 2 times 5, 3 times 6. Okay. So in general, you will be in N. U will be U1, U2, UN. V will be U dot V will be just U1, V1. Okay. Any question? I'm going to go a little bit fast because this is a little bit somewhat straightforward. These properties are very straightforward, so I just write it down quickly. The first one, basically you can swap the order. So scalar inner product is cumulative. You can swap the order. The second one is associative. You can actually distribute it. You can distribute this. The third one here is that you multiply by a constant. Okay. This is the same as do the dot product first and then multiply by a constant. Okay, some scalar. Now u dot u itself, u dot u is what? U dot u is actually u1 square plus u2 square plus un square, right? Of course, this is always bigger than 0. And this guy equal to 0 if and only if u is equal to 0. The only way to get the dot product to be 0 is the vector itself is 0. Okay. Any question about this? It's pretty straightforward. These properties we are going to, I just need to write it down. We're going to use it again and again. What it also says is that if I have a bunch of vectors, okay, if this guy dot w, you can actually distribute all of them. Okay, this will be C1, U1 dot W plus C2, U2 dot W. You can distribute all of them. Okay, and this we are going to use it again and again later. Any questions so far? Next, the concept of length. The length is also called the norm, N-O-R-M. It's also called the norm. It's just a mathematical name. It's basically the magnitude. It's basically the magnitude. In some books, it will be just like this. Okay, in our book, it has 2 more lines in it. It depends on the convention. Both notations are reasonable. Okay, our book uses this 2 bars on both sides. Okay. So this is actually the length. True or false? C is a scalar, so B is in Rn. C is scalar. What do you think? Is this true or false? You scale the vector, and then you take the length of the vector. Is it the same as you take the length of the vector first and then multiply by that scalar?
False.
False. Okay, good. It's false because, can you explain?
Because when you scale the vector, then you're multiplying all of the things inside it by that scalar, and then you're squaring all of those. And so you're adding more than if you just multiply the whole thing by the magnitude by c.
Okay.
That was a bad explanation.
Okay, it's okay. But it is false. Let's just take an example then, okay? Let's take a look at this example. CV will be 2, 2, right? So this guy will be square root of 2 squared plus 2 squared. Is it okay? How about if I take the magnitude first? Okay, C times this guy will be 2 times this. Also equal to 2. Now in this particular example, it works. When would it not work? So this is the answer is true that it is correct that it is false. But this example is not a counter example. What would be a counter example? You can think of this like this. You can just think of it geometrically in terms of a picture. Okay, in terms of a picture. So this is your V, which is 1, 1. If you scale it, make it twice as long. Okay, make it twice as long, and then you take the magnitude. Is it the same as you taking the magnitude first and scale it? For this example, it's true because C is equal to 2. Okay, C equal to 2. What happens if I have a picture like this? You scale it like this to this side, C equal to minus 2. Would this still work? What happens if C is equal to minus 2 instead? Minus 2 instead. If that one is minus 2, this one will be minus 2 minus 2. And then will be this. But this guy here will be minus 2, and you will get a minus here. And then they will not be equal. Is it okay? Do you guys get my point?
Yes.
Okay. So when C is negative, this doesn't work. When C is positive, it will work. Okay. Actually, I can modify this to make this work. Okay. I'm going to modify it to make this work. How do I modify it? I'm going to say that this guy is equal to this. Then it will work. That'll become true. Okay. Are you guys with me? I mean, if you think about geometrically what's going on, you can see that pretty easily. Okay. Because the multiply by a negative scalar, it turns it in the opposite direction. Okay. It's going to turn it in the opposite direction. Okay. Then the length is still positive. But then when you have, that's why you have the force is still positive. Okay. Okay. What is a unit vector? A unit vector means unit vector. What it means is that the norm of u, the magnitude of u is equal to 1. Okay? We want this to be equal to 1. So in general, it looks like this. U is equal to V divided by the magnitude of V. So this is the vector V. This is a vector V. So if you know how long it is, then just divide by that length. Then it will force it to be length 1. Okay. Unit vector means length 1. Okay. You basically take this guy and divide it by its own magnitude. Then it will just scale it down to now have length 1. So in this example here, so in this case, this guy will be my original V divided by square root of 1 square plus minus 2 square plus 2 square plus 0 square, which is going to be equal to 1 minus 2 to 0 divided by 3. Is it okay? So basically now I shorten the vector, but it's still in the same direction. Any questions so far? Okay, I'll just keep going. I'm going to go a little bit fast because these are kind of straightforward for now. Okay, so how do we do this problem? This is you just need to understand the terminology. It's really not that. It's pretty simple. So W is spanned by this guy. Okay. W is spanned by this vector X. You want to find a unit vector Z that is a basis for W. So Z is a basis for W. This is just really a straight line, right? It's spanned by one vector. So this vector Z, all I need to do is to make a unit vector out of this. How do I make a unit vector out of this? You have to do z divided by the magnitude of z, 2/3, 1, divided by this guy. It's not too exciting, this example. Okay. This is an x, sorry. Start out with the x. This is the x, okay? So the x, so this one will be, what is this? 4/9 plus 1. 13/3. Okay. Okay. Is it correct? Yeah. That's correct. Any questions so far? Next, we talk about the concept of distance. Distance between you and me. How is that defined? The distance between you and me is just this guy. This vector is b minus u. Okay. So the distance is just the, it's just the length of this vector. Just the length of this vector. So okay. Example. I'm going to go kind of go fast, but this is straightforward. Okay, very simple. Any questions so far?
How did you know that it was vector v minus vector u versus the other way around?
You can do the other way around. The distance, I mean, you can do the other way around because you square, it doesn't matter.
Right. Okay.
Yeah. You can do it either way. Orthogonal vectors. What does orthogonal mean? This just means perpendicular. It's just a mathematical term for perpendicular. Okay. So what's the condition? So if you have two vectors which are perpendicular, it looks like this. Now, if these two are perpendicular, then this one is going to be a rectangle. So this vector here, okay, and this vector here has the same length. Those two diagonal ones has the same length if this is perpendicular. Because it's the diagonal of a rectangle. If it's a parallelogram, it's not a rectangle, then these two are not the same length. Now, but this guy is u plus v, and this guy is u minus v. Okay? So perpendicular vector means that this length is equal to this length. Okay? So those two lengths has to be the same for this to be perpendicular. So if you do this, what is u plus v? U plus v is just this. This is saying that this guy dot is equal to this guy dot itself. This is the square of this, right? So this guy equal to this is the same as, okay, let me write one more step then. I will write one more step. These two equal means that if you square both sides, they are still equal. Okay, but what is the square of this guy? The square of the magnitude of a vector is going to be just this guy dot itself. Dot itself. This side guy, this is the square of the norm. The square of the norm is the vector of itself. Now, when you distribute this, you have u dot u, okay, plus 2 times u dot v. Because u dot v is the same as v dot u plus v dot v. On one side, on the other side, I will have u dot u minus 2uv plus v dot v. So you compare this equation, so some of these guys will cancel. This u dot u cancel with this u dot u, this guy cancel with this guy. Then you end up with 4 times u dot v is equal to 0, which means that u dot v is equal to 0. So this is the condition for two vectors being perpendicular. So two vectors are perpendicular if this is the condition. Okay? Condition for perpendicular is dot product equal to 0. And this is an explanation for that. Okay? And this works in Rn. Not just in R2, okay? In R3, R4, Rn. So this is an important result. Dot product equal to 0 means perpendicular. Any questions so far? Okay. Pythagoras theorem. So this is talk about in RM, we are basically generalizing all this stuff that we have learned in 2 dimension and 3 dimension in calculus 3 into something in n dimension, okay? Into something in higher dimension than 3. So we just talk about the concept of perpendicular is this, u dot v equal to 0. This is in RM, not just 2 and 3, okay? Pythagoras theorem, what does it say? Pythagoras theorem, you remember that in algebra we learned this, right? So this is a, b, and c squared equal to a squared plus b squared. Okay, the way in our terminology it look like this. Okay, in our terminology, so we have our u, we have our v. Okay, and this one will be u plus v. Okay. I mean, if you this v here is also the same as this v, right? So if you look at this triangle, here, this triangle will look like this triangle. Okay. So the theorem say that this length, the square of this hypotenuse, is just equal to square of this plus the square of the other side. Okay. So this is essentially this. We can actually prove it pretty easily. Okay, it's not difficult to prove. Oh, it's a proof. It's essentially this. The square of the norm of a vector is going to be equal to the vector dot itself. That's the definition of norm. Now you can just distribute this. When you distribute this, you will have u dot u plus 2 times u dot v plus v dot v. But this guy here is going to be the norm of u squared. Okay. And this guy is equal to 0, and only if okay, so we prove Pythagoras theorem. Okay, so when it's perpendicular, this guy is 0, so this guy is equal to this plus this. So which is really a generalization of this. Okay, so the form of the Pythagoras theorem now for us look like this. Look like this. This is Pythagoras theorem. How are we doing, guys?
Good.
Good.
Thank you. Concept of orthogonal complement. So now we are starting to get into stuff which is probably a little bit more interesting to you. So this is a concept. Let's say you have this is W. Okay, this is W. Let's say W is a plane in R3. Okay, this is W is a plane through origin in R3. A plane through the origin in R3 is a subspace. So this guy is a subspace. Okay. C is orthogonal. When we say a vector is orthogonal to a subspace, in this example will be orthogonal to the plane. That means it's perpendicular to every vector in the plane. So it will be this guy is called Z, and it's going to be perpendicular to the plane. In calculus 3, this will be called the normal vector, right? Normal also means perpendicular. So let's do an example. Okay. Find the vector C that is orthogonal to this entire plane. Okay. So the plane consists of all vectors X such that one, two, three, X1, X2, X3 equal to 0. That's what it means, right? So this one can be written like this in matrix form. And that means, this also means 1, 2, 3, dot, X1, X2, X3, equal to 0. So from this, can you pick out my vector Z? We want the Z to be orthogonal to every vector on the plane. Which vector is Z? No response. Can you see that this guy is my Z?
Yeah.
Is it okay? This is the vector that's perpendicular to every. It's just we're talking about the vector that is perpendicular to the solution set of this, to the solution set of this equation. But how do I describe the solution set? The solution set is the sub that is perpendicular to this guy. Okay, so this is my C. Okay. So my C can be equal is 1, 2, 3. Can I say my Z, can it be 2, 4, 6? 2, 4, 6 will also work, right? Okay. I mean, any scale multiple of 1, 2, 3 will work. Because your plane, you can scale the plane, you can multiply by 2, then this coefficient becomes 2, 4, 6. You have learned this in calculus 3. Just take out the coefficient, that's the direction of the vector perpendicular to this. So back to this picture again. Still this W. Now, if I think about the span of 1, 2, 3, what does the span of 1, 2, 3 mean? The span of 1, 2, 3, it's just the entire line, right? It's the entire line. This is the line. This guy is also a subspace. For this example, it's a subspace of R3. So you have originally this subspace, W. You have this other subspace. These two subspace has the property that this guy is perpendicular to the other one. Okay. We call this guy W perp. This thing here, these things here stands for perpendicular. It's like a stands for perpendicular because this is usually right angle like this. Okay, pronounce it as perp for perpendicular. So W perp is equal to this line. W is the original plane. Okay, so we have this terminology. So W perp is called the orthogonal complement. Of W. It's equal to the set of all vectors. So any questions so far, guys? I'm going to just keep moving. So in general, this does not have to occur in R3. Okay. So in general, W is a subspace of Rn. W curve is set of all vectors. I mean, this can occur in Rn basically. But conceptually, this is what's going on. The subject is perpendicular to it. Just take a guess on here. See, we can get some intuition. Okay. Let's see an example. Let's say R5. W is in R5. Dimension of W is equal to 3. So you have a 3-dimensional space in R5. What do you guys think is the dimension of W curve? All the stuff that are perpendicular to W.
Is it 2?
Yes, Anna. It's 5 minus 3. Just like here. Just like here. When you have, we will talk about this a little bit more. I just want to give you some intuition. Okay? So this will be a 2-dimensional plane. W curve will be a 2-dimensional plane in 5-dimensional space. Okay?
Yeah, I'm confused on what would that look like? A 2-dimensional plane perpendicular to a 3-dimensional object.
Yeah, it's difficult to imagine in 5-dimensional space.
Okay.
So every vector here in W. So if you really want to draw it, it's this something like this. Okay. So except one of these is actually 3-dimensional. You know what I'm talking about? It's not possible to draw it. Basically, any vector here, and any vector here are going to be perpendicular. That's what happens. It's not easy to picture because it's in 5 dimensions. Okay.
Okay.
I don't know whether I have a good way to explain it to you, but all the stuff, later on we'll have more examples. Later on I'll have a little bit more concrete example, okay? With a matrix. Okay. Yeah, I'm going to erase it. So I'm going to write down a bunch of properties. I'm not going to prove these guys, but it's pretty intuitive, okay? What do you think this is? W perp and then perp. You guys know what I'm talking about?
The W?
It's W itself. You guys know what this is saying? W perp is the stuff that is perpendicular to, let's say L is equal to W. curve, right? L, this is all the stuff perpendicular to W. Okay. And W will be all the stuff perpendicular to L. This is essentially the same thing. This is not transpose, this is curve. Okay. So L is equal to W, L equal to W. So this is the same as this. L equal to W per. Take this guy, put it in the L here. You will have W per. I probably should write down, this is the second one. The first one is W per is a subspace of Rn. I think I talked about that earlier, probably. That one is there. What do you think this guy? Can you guys take a guess about this? W intersection. Oh, you guys know this symbol? Intersection. Okay. You don't know that symbol. Okay.
It's the overlap, right?
It's the overlap. Yeah. This means that the overlap is the overlap of these two guys. Okay. The overlap. Okay. This is intersection. Intersection of the two subspace.
So we doing set theory, huh?
It's set theory, yeah. You have intersect and you have union. Union, you have seen that. This union thing, you have seen that when you put intervals together. Okay. So what's the intersection of W and W per? Okay. It's actually equal to the zero vector. Only the zero vector can be both. Okay. Because the intersection of these two, if you are in both W and W per, that means W is in both, right? This little w is in, or maybe I call this X then. X in W and X in W per. X in W and X in W per. That means this X is in both. That means X is perpendicular to itself. Perpendicular to itself, which means that X dot X is equal to 0. What vector will have X dot X equal to 0? We talked about it a little bit earlier, about maybe half an hour ago. The vector whose length is equal to 0 has to be the 0 vector. Okay? So that intersection is the 0 vector. Okay. So I can now give a little bit more concrete example. Okay? We're going to give a little bit more concrete example. Any questions so far? We are going to take the remaining 9 minutes to give a more concrete example.
So if W isn't a subspace of Rn, can we not do this stuff?
Yeah, you cannot do that. The definition is assuming that you start out with W a subspace.
Okay.
Yeah, W is a subspace. And then W per is also a subspace. Okay? Consider this matrix. You remember what column space mean and null space? Column space and null space. I assume that you know what that means. Okay. Column space is the span by the columns of A. Null space is the solution of AX equal to 0. We have done this many times. Okay. So column space is a subspace in R. What should I put in that box? What should I put in that box? R3 or R5? No?
5.
5? Span by the columns. How many entries are in each column? You guys know this.
3.
3. You guys were able to do this type of problem in the test. Null space is a subspace of it's a subspace in okay, because you're solving AX equal to 0, you're doing this. Okay. Okay. I need to talk about the concept of row space instead of column space. Concept of row space. For this matrix, row 1 is actually this row, but if you want to write it as a vector, it's this guy. Row 2. So the row space of A, which is written as row A, is the span of those 3 vectors. Do you guys understand what I'm trying to get at? The concept of row space? Row space is spanned by the rows of A. Column space is spanned by the columns of A. So this one is a, so this is a subspace in what? R3 or R5?
R5.
R5, yes, 5 entries. Okay. Now, I want to convince you something here. Okay. So when we solve AX equal to 0, okay, it's the same as log for X in R5 and is perpendicular to rows of A. Can you guys see that? So when I solve this guy times X equal to 0. When I solve this, I get the null space, right? Solve for AX equal to 0. the null space is the solution set for Ax equal to 0. Okay. Solution set is equal to the null space of A. Okay. So when I told this is important, this is, I mean, I may have to repeat it next time. When you solve this to find the null space of A, you are actually looking at for the vectors which are perpendicular to the rows of A. Okay. Can you guys see that? Because when I solve it, I'm doing this dot product equal to 0. This dot product equal to 0. Oh, there's only 3 0 here, not 5. Sorry. Mess up. Only 3 zeros here. And the third one, not this one, equal to 0. So what I have just explained to you, okay, the null space of A, I just explained to you this. The null space of A consists of all the vectors that are perpendicular to the rows of A. Null space of A is the perp of the row space of A. Okay, we finally get to something that is more interesting. Okay, so I should stop here. And next time I probably repeat this example. Okay, but the main thing is that you have this, and then we can play around with this and then get some more stuff. Okay, the null space of A is the orthogonal complement of the row space of A. Now both of these are in R5. The row space of A is in R5. Its orthogonal complement is also in R5. Null space of A in R5. Okay. So when we find null space, we are trying to actually finding the vectors which are perpendicular to all the rows of A. Okay, I will stop here. Do you guys have any questions? No questions? We will repeat this example next time, and then also expand it a little bit to make some more comments about it. Any questions? Okay. Anything else? Is it hard? No?
It's okay.
It's okay. All right.
I
Thank
won't
you.
know, I won't know until I do the homework.
Okay.
Yeah.
You can start to do the homework. I'm really done with this section. I go pretty fast, but like at the beginning of the chapter, usually I go fast. Okay. Because there's not a lot going on there. Okay. So I'll see you again on Wednesday. Okay.
Thank
Bye.
you.
Have a
Thank
good day.
you.
Bye.
Bye. Bye.